Biosensor Principles in Microfluidics. This lecture is meant to give a brief overview of biosensor design principles, as well as introduce biosensors commonly used in point-of-care testing. This is followed by an introduction into the design considerations surrounding microfluidics, including fabrication, fluid transport, valves, and mixing. My name is Keith Brock. This lecture is brought to you by the University of California, Davis, Lawrence Livermore National Laboratory's Point-of-Care Technology Center. The UC Davis LL&L Point-of-Care Technology Center has no financial interest in any of the companies represented in this educational tool. The information contained in this training video is educational and intended for informational purposes only. Always consult the vendor-approved instruction manual prior to performing any point-of-care test. The International Union of Pure and Applied Chemistry defines a biosensor as a self-contained integrated device which is capable of providing specific quantitative or semi-quantitative analytical information using a biological recognition element which is in direct spatial contact with a transducer element. Or, simply put, a biosensor is any analytical device which converts a biological response into an electrical signal. Typical biological responses may include hormones, electrolytes, neurological signals, or enzymes. This slide illustrates the generic elements of a biosensor. Number 1, the biochemical recognition element. Often this will include a selectively permeable membrane. Number 2 is the transducer element, which converts the biochemical event to an electrical signal. Most common biosensor transducers include electrochemical and optical transducers, which we will discuss in detail later in this lecture. Less common biosensor transducers include piezoelectric, thermo, or magnetic transducers. Element number 3 is amplification, wherein your biosensor will increase the power of the signal using an external power supply. Element number 4 is signal processor, where your biosensor will filter and interpret the electrical signal into a clinically meaningful value. Element number 5 is the display, wherein your biosensor will project this value as a digital readout. All measurement signals are corrupted by noise. Noise is defined as unwanted signals introduced to the system by outside sources, for example, power lines, radio or television, electromagnetic waves. Filters are used to reduce noise and maximize the signal-to-noise ratio. Once the signal-to-noise ratio is optimized, the biosensor output can be normalized with respect to the noise of the system. The resulting normalized data focuses on the biological response of interest. The biosensor transfer function is a mathematical model that defines the relationship between the output projected on the display and the input electrical signal developed by the transducer of a linear system. The dynamic range of a biosensor refers to the range of input signal amplitudes over which an electronic device will operate within a set of specific parameters. The signal resolution refers to the fineness of detail in the measurement. For continuous systems, the signal resolution defines the minimum increment that can be discerned. While there are many types of biosensors both on the market or in development, for the purposes of this lecture, we will focus on 3. Amperometric biosensors, optical biosensors, and potentiometric biosensors are the most commonly used in point-of-care testing. Point-of-care testing is defined as testing at or near the site of patient care. Dr. Leland Clark is credited with the invention of the first biosensor. On his closet shelf in October of 1954, Dr. Clark curated the oxygen electrode. 10 years later, Dr. Clark used the same glucose oxidase enzyme and reversed the polarity of the platinum electrode to create the first amperometric glucose biosensor. Since then, recent market projections expect the glucose monitoring device industry to exceed $18 billion in 2015. Simply put, the governing principle of amperometry is as follows. When provided with a constant driving potential, the analyte bound to the receptor will undergo an oxidation reaction that can be quantified by measuring the electron exchange from the working electrode, or the anode, to the counter electrode, or the cathode. This electron exchange, or current, is limited by the diffusion of the analyte through a selectively permeable membrane and various boundary layer phenomena, but in a well-designed test strip will be linearly proportional to the concentration of target analyte. Amperometry is most commonly and famously found in glucose monitoring systems. This figure illustrates the chemical reactions involving glucose dehydrogenase and ultimate generation of electrons to generate the current, which is measured by the glucose meter. Here we have illustrated a glucose and lactate tri-layer biosensor. The outer membrane prevents large objects such as red blood cells and proteins from entering the sensor, while allowing glucose or lactate to enter and react with the enzyme layer. The enzyme layer generates hydrogen peroxide, which diffuses through the inner membrane and interacts with the platinum anode to yield electrons. Optically based biosensors use the difference in wavelength, angle of refraction, phase change, or percent transmission between the initial incident light and reflected light to measure a target analyte. Though outside the scope of this lecture, our center partners at the Center for Biophotonics Science and Technology specialize in the research, development, and application of new optical tools and technologies applied in medicine and the life sciences. Pulse oximetry functions by measuring the difference in the visible and near-infrared absorbance of fully oxygenated and deoxygenated blood. Because of its continuous, non-invasive, and instantaneous measurement of blood oxygenation, pulse oximetry is currently used extensively in hospital settings. Another example of an optically based biosensor is the hemoglobin meter. This biosensor functions using target-specific enzyme coupled to a dye. The color change measured by light absorption is proportional to the concentration of the target. In the case of the hemoglobin meter, rapid diagnosis of anemia, both in routine patient care or urgent or emergency department settings, can be accomplished in seconds. Target-specific enzymes coupled to a chemical dye is illustrated on the lower right-hand corner. As the reaction proceeds, there is a color change relative to the concentration of the target found in the sample. The color intensity is measured by a photometric method wherein the difference in transmitted wavelength is calculated and interpreted. The beer-lambert law also governs the principle by which blood oxygenation is measured by pulse oximetry, illustrated on the right. According to the beer-lambert equation, the absorption of light is proportional to the path length, L, the concentration of absorbing species in the material, C, and the molar absorptivity, epsilon. Now we will see if we can apply the beer-lambert equation in an example problem. Given the total absorbance through the glass channel, or A total, the absorptivity of the glass, epsilon glass, and the concentration of absorbing substances in the glass, C glass, calculate the concentration of absorbing species in the sample buffer solution flowing through the glass channel. First, calculate the absorptivity of the glass. The absorptivity constant is given to be 2 liters per mole centimeter, times the path length through a single layer of glass, or 0.25 centimeters, times the concentration of absorbing species of glass, or 1. Multiply this answer by 2 since the path of light goes through 2 layers of glass. The glass component of the total absorptivity is found to be 1. Next, solve for the sample plus buffer component of the total absorptivity. The sample plus buffer component of the total absorptivity is found to be 9. Solve the Beer-Lambert equation for the concentration of absorbing substances and plug in the absorptivity constant for our sample plus buffer solution and the path length through the sample plus buffer. The concentration of absorbing species in the buffer plus sample solution is found to be 0.6 moles per liter. Potentiometric biosensors are used extensively in clinical chemistry, specifically when measuring electrolytes. These biosensors simply measure an electrical potential difference between 2 electrodes. Here, Dr. Yang et al. Have recently characterized potentiometric, amperometric, and optical biosensors embedded in the elastic waist of underwear under tight direct contact with skin. In this paper, the textile-based carbon electrodes have been shown to accurately measure hydrogen peroxide, dipotassium salt, and ferrocyanide. The potentiometric biosensor simply measures an electrical potential difference between two electrodes. These electrodes consist of a transducer and a reference that are connected electrically through the sample in a potentiometric circuit that behaves according to the Nernst equation. The Nernst equation shows that the potential difference, or V ion, is proportional to the Boltzmann constant, temperature, the charge of the ion, and the natural log of the ion concentration gradient. For measuring electrolytes such as sodium, potassium, calcium, or chloride, ion-selective electrodes are used. The Clark electrode tests for partial pressure of oxygen. The current generated is proportional to the partial pressure of oxygen diffusing to the electrodes. Once again, let's try to apply what we have learned. The relative concentration of sodium ions both inside, B, and outside, A, the membrane, are 50 millimolar and 460 millimolar, respectively. Using the Nernst equation, solve for the electrode potential in millivolts. Note that K times T equals 61 millivolts. To solve for the sodium ion potential across the membrane, plug in 61 for the Boltzmann constant times the temperature, then plug in the charge associated with the sodium ion, or positive 1. Always be sure to incorporate the sign of the ion in question. Next, plug in the concentration gradient of sodium. The sodium ion potential across the membrane is found to be 134.4 millivolts. Microfluidics is the study of the behavior, control, and manipulation of fluids on a sub-millimeter scale. The 1949 inkjet patent described a method by which micro volumes of ink could be selectively deposited on paper. Today, the application of microfluidics is used to create fully integrated devices performing several laboratory functions on a single chip, only a few centimeters in size. The miniaturization of diagnostic technologies has been driven by the high cost of purchasing and maintaining fully equipped laboratory-based instruments. Historically, the high cost associated with personnel and reagents, the impracticality of instrument support, and the physical distance between the test and patient have driven up the cost per test. Consequently, the purchasing of new laboratory equipment has been largely based on the projected volume of testing. Replacing fiscal decision criteria with needs-based or impact-based criteria, miniaturized diagnostic laboratories show promise to be cost-effective through low initial and reagent costs, and versatile, consuming little to no energy, resulting in affordable, low-cost diagnostic testing. This, of course, can have profound implications on otherwise underserved patient populations. Microfabrication of miniaturized diagnostic tests has been heavily influenced by the semiconductor and microelectromechanical industries. Common microfluidic fabrication methods include photolithography, embossing, and injection molding. The fabrication method is determined by the material of choice, the cost and speed of fabrication, and the design specifications. Photolithography, or light printing, is the process by which thin silicon wafers are patterned using a photoactive polymer, also known as photoresist. Polydimethylsiloxane, or PDMS, molds can be replicated using this silicon master. Using this well-established method, one mask can make hundreds of wafers, and one wafer can make multiple molds, with tolerances limited by the wavelength of light. One disadvantage of photolithography is the environment in which the mask must be created. Defects or dirt on the mask will ultimately transfer the defect to your designed wafer. This slide illustrates the steps involved in photolithography. First, the metal-coated silicon wafer is spin-coated with photoresist. Once exposed to the light-sensitive photoresist is degraded according to the shapes projected by the mask. Through a process of wet or dry etching, the metal layer is shaped to reflect the geometries made by the photoresist. Embossing is a technique that uses heat and pressure to shape thermoplastic materials against a master or a stamp pattern. With access to a hydraulic press, the advantages of embossing are that it is relatively cheap and fast, though the fabrication of the stamp may be expensive and time-consuming. Injection molding is a practice commonly used in the plastics industry. Here, pellets of thermoplastic are melted and injected under high pressure into heated mold cavities. Once cooled, the newly formed part is released from the mold. Advantages of injection molding are excellent contact with features of the mold and higher throughput than embossing. Consequences of injection molding include the quality of the replica depends on the quality of the master, and that it's not ideal for prototyping. Basic components of microfluidic devices covered in this lecture include pumps, valves, and mixers, of which there have been many types described in many publications. These components are combined to build application-specific microfluidic systems. For pressure-driven microfluidic systems, such as those using syringe or vacuum pumps, the pressure differential necessary becomes much higher at a microfluidic scale. The flow rate, Q, is proportional to the pressure differential, delta P, and the radius of the channel to the fourth power. So, for a tube diameter decreased by a factor of 100, such as 1 centimeter to 100 micrometers, the change in pressure necessary to maintain the same flow rate must increase by a factor of 10 to the 8th. In contrast, electroosmotic flow is based on the movement of the bulk solution in response to the movement of counter ions near the surface of the channel walls in the direction of an electric field. Advantages of electroosmotic flow include its distinct flat flow profile, minimizing dispersion. One example of active gating microfluidic valves involves the layering of two polydimethyl siloxane, or PDMS, layers on a planar glass substrate. The top layer houses the pneumatic controls while the bottom layer houses the fluidic channels. One can easily see how pumps and mixers can be created using a series of similar pneumatically controlled configurations. Passive gating can be achieved using capillary burst valves. In this example, fluid driven by centrifugal force is controlled by A sudden expansion in the microfluidic channel, B, a hydrophobic coating on the channel wall, both where the rotational speed must exceed the burst frequency for fluid to continue, or C, a hydrophilic U-shaped siphon channel, where the rotational speed must exceed the burst frequency for fluid to stop. In order to better understand microfluidic mixing, a brief overview of laminar and turbulent flow may be helpful. A Reynolds number less than 2,130 will ideally result in laminar flow, while a Reynolds number greater than 4,000 ideally results in turbulent flow. Fluidic mixing is most quickly and efficiently achieved in turbulent flow systems. Reynolds number is calculated by multiplying the density of the fluid, the average velocity of the fluid in the direction of the flow, and the diameter of the channel divided by the viscosity of the fluid. So, as the diameter of the channel becomes smaller, so must the Reynolds number. Typical Reynolds numbers in microfluidic systems are less than 1, making microfluidic mixing difficult. Microfluidic mixing is typically limited by diffusion, or the spread of particles through random motion from regions of higher concentration to regions of lower concentration. Diffusion can be modeled using the top equation, where x is the diffusion distance, d is the diffusivity constant, and t is time. To speed diffusion mixing, researchers have developed unique three-dimensional serpentine microchannels to encourage chaotic advection. Today, multiple types of micropumps, mixers, and microvalves have been developed by thousands of researchers with little to no standards defined for interconnectability. It is no longer enough to design an elegant microfluidic component. The future of microfluidics is a platform that provides easy combination of reliable components universally integrated using well-defined, low-cost fabrication technology. Researchers are now moving their focus towards the application of microfluidic systems that incorporate strategic biosensors to address high-impact clinical needs.